Hey everybody, in this video, we are going to talk about many things regarding the solubility of salts. But before we begin, we need to talk about a few things. The first thing I want to talk about is the self-ionization constant for water at 25 degrees Celsius, and this will be discussed further in Unit 12. So, the self-ionization constant for water is Kw. It describes the K for when water splits itself into H plus and OH minus. So, the Kw turns out to be 1 times 10 to the negative 14, and we know that the Kw is simply just the equilibrium expression for the reaction, so it will be H plus times OH minus. And as you notice, it is a pretty small number, and because K is a small number, we can conclude that water doesn't really like splitting into H plus and OH minus, because a low K means that the reaction likes to stay as reactants and not products. So essentially, we use the Kw to describe the equilibrium between hydrogen ions and hydroxide ions in water. And again, this will be discussed in further detail in Unit 12. Now let's move on to a topic called complex ions. A complex ion is an ion in solution that forms when an ion, which usually tends to be a metal cation, is attached to other molecules or ions which are called ligands. The bonds that form between the central ion and the surrounding ligands are called coordinate covalent bonds. Now you see the word covalent bonds, so it's a type of covalent bond, but it's a coordinate covalent bond. Now these types of bonds form when the ligand donates its electron pair to form a covalent bond. So normally what happens is that atoms each donate 1 electron to form a bond, but this time for a coordinate covalent bond, the ligand decides to donate all of the electrons to form that bond. Now why might this happen? Well, if you think about it, let's take a look at this picture where we have a bunch of waters, which will be our ligands, and the aluminum 3 plus in the middle will be our central ion. Notice how the central ion is positively charged, and these electron pairs are negatively charged, so they're naturally attracted to the ion, and they might want to form a bond. But the other reason why a coordinate covalent bond forms instead of simply a normal covalent bond is because aluminum 3 plus already has an octet, because after losing 3 valence electrons, it has an octet, and it's happy. So why does it want to form bonds? And we don't usually see metals forming bonds, so why would aluminum 3 plus want to give up any electrons to form a bond when it's already stable? So because of that, the waters have to do all the work to make the bond, and the aluminum's like, sure, you could bond with me. It doesn't really matter because I'm already stable, but I'm not willing to put any electrons into the bond that you are going to make. So that's an easy way of understanding why these things happen. Now, each of these waters have 2 lone pairs, and one of the lone pairs might decide to form a bond with aluminum, and in the end, all 6 of these waters will donate 1 lone pair to form a coordinate covalent bond. And as shown here, these are your 6 coordinate covalent bonds that are formed. And notice how this shape is octahedral, because there is 1 atom in the middle attached to 6 things, so it has a steric number of 6. So keep a note of that, and remember your electron geometry and your molecular geometry as well. So now let's talk about some ligands that we can have. So for the ligands, we can have water, of course, but what about the other ones? Well, here's a cool list of every single, well, not every single, but many of the ligands that you can have. So we could have the fluoride, the chloride, the bromide, the hydroxide, the cyanide, the oxalate, and some neutral compounds as well, such as ammonia, water, carbon monoxide, oxygen gas, and nitric oxide. Now, complex ions will be discussed in a future unit in way more detail than what we're doing here. So for now, just know these things, and let's move on. So the true topic we are going over today is what are the two ways, well there are more ways, but we're going to talk about two, that we can get insoluble salts to dissolve in water. So let's do a little case study and let's investigate zinc hydroxide. Zinc hydroxide is relatively insoluble with a KSP of 4 times 10 to the negative 17, and this means that it does not want to dissolve. So the first way we can get things to dissolve is to add a strong acid. Well, it could just be any acid, so adding acids would be fine. So adding acids to basic salts will dissolve them, or in other words, basic salts dissolve better in acidic environments. Now let's employ our knowledge of equilibrium to know why this is true. So this is the KSP reaction, and here's the KSP, and notice how it has a low KSP, so the reaction doesn't really like going to the products, and that's why zinc hydroxide is pretty insoluble. Now, we have to combine reactions in order to prove this, and we will start off with the self-ionization of water, which we know has a Kw of 10 to the negative 14. Now we flip the reaction, and we know that flipping reactions makes the K become inverted, so it will be 1 over Kw, which turns out to be 1 times 10 to the 14. And then we are going to double our reaction in order to cancel out the OHs on each side, as you will see soon. So we have to cancel it, so we multiply by 2, and we have to square our K. So our K was 1 over Kw, but we have to square that, so it would be 1 over Kw, all that squared. And it turns out that the K for this reaction over here is 1 times 10 to the 28 power. So we can actually add these two reactions together, reaction 1 and reaction 2, to form reaction 3. And notice how our hydroxides cancel out, leaving 2H plus and ZnOH2 on the left side, and on the right side we're left with Zn2 plus and let's see, 2H2O. So this is your reaction, and remember, when you add two reactions together, their K's are multiplied, so the K for this is this, and the K for this is this. So we have to multiply the KSP times 10 to the 28. So the K is equal to 4 times 10 to the negative 17 times 1 times 10 to the 28. And we get that the K for the new reaction up here is going to be 4 times 10 to the 11. So it seems like this reaction is telling us that if we mix the solid zinc hydroxide with some acid, which is represented by H+, since acids release H+, then it will turn into these two, and it says that the K is pretty high, which means that in the presence of a significant amount of acid, we can actually get a lot of products compared to reactants. Or in other words, the zinc hydroxide will want to become products since the K is so high, in the presence of acid, of course. So let's read this nice paragraph that I wrote. So, initially, at equilibrium in pure water that is not acidified yet, zinc hydroxide is not very soluble and has a low KSP, as H+ is very low, and because it is very low, that means that the reaction above, which is in green, won't go to the right very much with a very low H+. So remember, the more H+ you have here, the more you are able to form the products, since if you don't have H+, you can't form the products in the first place. And in addition, if you have too little products, such as in pure water, where the concentration of H+, as you will learn later, is 10 to the negative 7 molar, you will have most of your reactions staying on the left side, even though the K is super high. The K is super high, but you have so little reactants that the reaction will stay on the left side until you have more reactants. So, however, with a high concentration of acid or H+, zinc hydroxide is more soluble, because if you think about it, now that we have more H+, so let's just say 10 to the 1 molar perhaps, then the higher H+ will shift the equilibrium to the right, and this is Le Chatelier's principle, remember? and this moves the reaction forwards. So if the reaction here goes forwards, we will get the zinc hydroxide to start dissolving more. So in general, by increasing the concentration of the H+, we will move the reaction to the right, and zinc hydroxide will dissolve better. Hopefully that made a lot of sense, and now let's talk about an exception. Adding acid to a non-basic salt will not dissolve it. So before, our basic salt was zinc hydroxide because the hydroxide ion is soluble, and from the last video, or the last 2 videos ago, I told you that all the metal hydroxides are strong bases. So let's take a look at something that's not a basic salt. For example, silver chloride. Silver is not a base, chloride is not a base, and because of that, it's a non-basic salt. And non-basic salts like silver chloride will not dissolve better in acidic conditions. Let me prove this to you. So here's the KSP reaction, and we know that the KSP for AgCl, an insoluble salt under normal conditions in pure water, is super duper small. Now we can write a second reaction where, just like how we converted water into H+, we can actually convert HCl into H+ and Cl-. As you know, this is a strong acid, and since it is a strong acid, it will want to become H+ immediately upon touching water. And because of that, K is super big for this reaction. Now what if we flipped it? Well, we flipped it. It will be 1 over K, and since 1 over something super big is super small, the new K will be super small. So, if we combine the 2 reactions together, we can see that the Cl's cancel out, leaving silver chloride plus H+ becomes HCl plus Ag+. Now, what's the K of this new reaction? Well, by adding 2 reactions together, we multiply their Ks. The K for the first one was small. The K for the second one was also small. Small times small is very small. And we're doing general terms, but trust me, it is very small. And we don't even need numbers because something that's super small for K means that the reaction will not move forwards no matter how much reactants you have, since the K tells us the ratio between the products and reactants. And if it's super small, that means that no matter what, you will have a lot of reactants in the end. So, because of this, adding any amount of H+ or acid won't shift the reaction right appreciably, but it will shift it a little bit, but just not appreciably, since the reaction tends to like reactants due to the low K. Now let's talk about the second way we can dissolve very insoluble salts, such as zinc hydroxide. We can add a complexing agent, or in other words, some ligands, to dissolve the salt. And note that you need enough ligands for this to happen. Now, we have zinc hydroxide here turning into its ions, and the KSP is super small. Now, if you didn't know, you will know now. When a metal cation and some ligands combine together, it's actually a very spontaneous process most of the time, and that's why when you add a complexing agent such as ammonia to zinc, it will combine and form this cool complex. Now you're like, how does this have a +2 charge? Well, zinc has a +2 charge, and the ammonias have a neutral charge. 2 plus neutral is 2. So that's why this complex ion has a 2+ charge. Now, notice how the K is super high. This just proves that this reaction is very spontaneous and likes to form the products. So because K is high, this reaction will tend to want to make these complex ions, and the formation of a complex ion from a metal cation and its ligands is called Kf, or the K of formation. So we just learned a new type of K here. Yay. Now, how do you know how many ligands attach to the metal cation? Well, here's a way to think about it. Double the charge to get the coordination number, or the number of ligands for now. So, for now, think of the coordination number as the number of ligands attached to the cation. Since zinc has a +2 charge, +2 times 2 is 4 ligands, or a coordination number of 4, and thus we will need 4 NH3s since each NH3 is 1 ligand. So now let's do some more reaction combining, and you see that our zinc will cancel out, and we are left with all this. Now, how do we get the K of this? Well, we multiply the KSP times the KF to get the K of this reaction. And it turns out the K of this new reaction, where you get zinc hydroxide, mix it with some ammonia to get some complex ions, is actually 1 times 10 to the negative 8. By adding ammonia, the K of dissolving zinc hydroxide solid just increased from 4 times 10 to the negative 17, as shown here, to 1 times 10 to the negative 8. That's a huge difference, about 10 to the 9 times as much, by the way, and this leads to more zinc hydroxide dissolving and favoring the products. Since if you think about it, if we go from a low K, such as 4 times 10 to the negative 17, to a higher K, 1 times 10 to the negative 8, once you add the ammonia, of course, then you will get more products, since the K just went up, and that means more things will dissolve, and that means the solubility of zinc hydroxide in ammonia will increase. Now, if you notice, the higher the concentration of ammonia, the more it will dissolve. So keep a note of that, and that also applies for the acidic situation too, where having more H+ will yield more dissolved zinc hydroxide. So just keep a note of that. And that's all for this video. I hope you learned a lot, and have a nice day, everybody.